So today we are thrilled to have Dr. Molina join us. Dr. Molina is a project scientist working for the Cooperative Agreement to Analyze Variability, Change, and Predictability in the Earth System, also known as CATALYST, and the Climate Change Research Section at the Climate and Global Dynamics Laboratory in NCAR. She obtained her PhD in Earth and Ecosystem Science from Central Michigan University, a master in climate and society from Columbia University in New York, and her Bachelor of Science in Meteorology from Florida State University. An interesting fact is that Dr. Molina has been a certified broadcast meteorologist for almost 10 years now, and she was the youngest broadcast meteorologist on American cable news at 23 years old, which is a pretty impressive achievement. Additionally, she serves on numerous AMS conference committees and routinely helps teaching artificial intelligence applied to meteorology and subseasonal to seasonal prediction. She has numerous awards and travel grants that would be too long to list today, but most notably, she was an advanced study program postdoctoral fellow at the National Center for Atmospheric Research, and she obtains the student best oral presentation at the AMS conference on severe local storms. And today she is going to tell us about some of her recent work at NCAR about uncovering and predicting patterns in large climate data using both supervised and unsupervised machine learning. And with that, I'll hand it over to Dr. Molina. Thank you for joining us today.
Thank you so much for that wonderful introduction, Tom. It's not often that my background in broadcast meteorology is mentioned before giving a talk, so I appreciate that. So the work that I am sharing with you today is funded by the U.S. Department of Energy, and a key component of this work lies in using machine learning to better understand the predictability of large-scale climate patterns and modes of variability. So as Tom mentioned, our group is called CATALYST. So it's a cooperative agreement funded by DOE, and I work within the climate change research section at NCAR. I'd like to acknowledge my co-authors on this work. So they are Aishu, Yaga, Jerry, Sasha, and Katie Dagan. And I'd also like to acknowledge some collaborators from CSU, so Colorado State University, including Kirsten and Zane, who have been very helpful with some of the S2S work and helping me get moving and making progress in that direction. But some of the work that I will be sharing with you is also in very early stages. So I look forward to receiving feedback or suggestions for improvement from all of you, and also welcome collaboration. So we know that there has been a lot of very recent advances in deep learning, machine learning, and also some technology that has really enabled this growth and these breakthroughs in our ability to apply some of these techniques to Earth system science. And a lot of these advances have taken place in industry. So products that perform facial recognition have been making tremendous progress. We also have self-driving cars. And so a lot of those advances are because of deep learning, and also a growth in data and also hardware development. So it's really this this intersection between data growth, hardware development, and machine learning advances in algorithms that have enabled a lot of this growth. As many of you who are in this audience likely already know, machine learning is a subset of AI, and the term machine learning was actually coined quite some time ago in the late 1950s by Arthur Lee Samuel. And that person was a computer scientist and pioneer in machine learning, and ML was defined as the ability of computers to learn from data. And now we have deep learning, which is a subset of machine learning, and that is specifically focusing on models that use artificial neural networks and that are typically of several layers deep. And so all of these advances that have taken place in industry for some of these technologies that we use every single day can really be leveraged to better understand climate variability and predictability, and help us better understand just our Earth system overall. But as I mentioned, machine learning really has a long and rich history. It dates back to the 1950s, so this isn't really a new topic. For example, in the 1950s, we saw quite a few developments, including a key one, which is the development of the perceptron algorithm. And that was a precursor to modern neural networks. The 1980s also saw tremendous progress, including the development of the backpropagation algorithm. And the development of that algorithm is what enables us to have models that are several layers deep. There were also some periods of little progress or limited progress, and those are typically referred to as the AI winters. So roughly in the 1970s and 1990s, there was a lot of skepticism due to limited progress and limited technology in this field, and so there was reduced funding. And so again, those are typically referred to as the AI winters. And so really what has brought us to the point where we are today were a lot of recent advances that occurred in the 2000s. But before we get to that, in 1998, there was a paper published on convolutional neural networks, and it wasn't the first paper, but it is certainly an important one. And moving forward from there, there was the development of a very large data set that consisted of labeled data and very high quality. And so this groundbreaking data set consisted of over 14 million high quality labeled images for over 22,000 categories. And so this data set was ideal for training models in your supervised learning framework, where you have a label associated with some input for your model. And so essentially you have the answer to the question that you're posing to this model, and that enables this model to learn those answers and then hopefully generalize to data that we don't know the answer to. And so this high quality data set that was developed was called the ImageNet database, and it was worked on for several years. It was a huge effort. And then it was, the objective of it was to benchmark model development and overcome some of those challenges with model overfitting, and also just to benchmark some of these algorithms that were being developed. And so then that started the ImageNet Large-Scale Visual Recognition Challenge. And in 2012, there was a winning model that was very important and a key advancement. And that was just a convolutional neural network that was quite deep. It had several layers, and that's what was attributed to that large drop in error that won that contest that year. Since then, there have been continued advancements, and that error has continued to drop. But because there was that particular year and that convolutional network with several layers deep, we really started to realize that as we increase the number of layers into our models, potentially the greater the ability for them to learn and perform better. And what enables that is the development of technology and hardware such as GPUs that make it much faster for us to make these sorts of computations for our models. And I would also argue that software development has also really enabled this progress in our ability to use some of these tools for Earth system science, particularly software that's open source, such as Python. And so here, this plot, I really like it, probably too much, but it's just essentially a fun way to visualize trends. And this tool is called just your Stack Overflow Trends. And if you're not familiar with the website, Stack Overflow is a question and answer website for computer programmers, where computer programmers can learn from each other by posing questions that they have, or I guess I have, since I also pose questions on that website, and also try to figure out ways to answer the questions that perhaps others have and I may already know the answer to. So it's really this conversation that's ongoing across the internet on code. And the registered user base is over 10 million, and there are about 8,000 questions asked per day. But using this tool, we can track user interests on specific programming languages. And we can see that just in the last couple of years, Python has become the most popular language, again, at least according to this tool. And it's really been on that upward trend over the last several years. And we know that Python's large user base this makes that evident. There's a lot of people using that. There are a lot of open source packages that have been developed and written in Python, or at least that Python wraps around. And so that really enables this explosion and growth in a specific software programming language. And a lot of our machine learning and deep learning libraries are written in Python. And so really we have this relationship where open source packages are freely available on the internet. We have a lot of tutorial materials, examples, and we can ask each other questions on how to code a specific deep learning model for our specific application. And that's really, I think, enabled this breakthrough that we're in now, where we're able to apply these tools and very advanced tools for our specific questions and leverage them for Earth system science. So hopefully this continues to enable the discovery of meaningful patterns in data and information for public good. And so now I'll switch gears to our specific questions that we are using some of these tools for. And so the first project that I'm sharing with you is a paper that's currently under review in Journal of Climate. And if you read the Washington Post or follow Capital Weather Gang, you would perhaps have seen a recent story that came out, and the headline is quite scary, essentially discussing that the Atlantic meridional overturning circulation is reported to be in the weakest it has been in the last millennium. And what is the overturning circulation in the Atlantic? Well, that's a large-scale ocean circulation. It redistributes heat from low to high latitudes, and we know that the influence of AMOC is widespread across the world. So it can affect sea surface temperatures in different basins, particularly in the North Atlantic, which can then influence downstream climate over places like Europe. We also know that it has an influence on the El Niño Southern Oscillation across the tropical Pacific, and it has been associated with past abrupt climate change events. And so this is a really important, perhaps, thermometer into how our climate is doing and potential changes that can occur down the road, and potentially some tipping points that could be associated with this circulation. And essentially, it just transports heat from lower latitudes to higher latitudes, and there is deep water formation that occurs in the North Atlantic. And so this is really, again, an important circulation across the world. We do know that AMOC is projected to weaken under both low and high emission scenarios. And there are also several studies that have suggested that there is an asynchronous relationship between the Atlantic and the Pacific, meaning that there has been in the past a Pacific deep meridional overturning circulation, so deep water formation in the North Pacific, which is not really occurring right now. There's a lot of fresh water in place out there. And so it's been suggested by previous studies that there's an asynchronous relationship between these two basins, that potentially, if we're seeing a slowdown in the North Atlantic, we could see an increase in the North Pacific in deep water formation. And so the concern there is, again, we could be seeing all kinds of ramifications to the global climate, in addition to greenhouse gas, or the signal from greenhouse gases. And so a question that we posed in this project was whether, what would happen to global sea surface temperatures as a result of an AMOC collapse or shutdown as it continues to slow and eventually potentially collapses. And then the other question was, what would happen to global SSTs and ENSO if the Pacific deep water formation started? So we're looking at these relationships with very long simulations that spanned about 800 years. And then we perform various analyses. And so here I focus on using signal processing. These are not new algorithms or techniques. They've been around for quite some time, but they are very powerful. And I think that if we can visualize them creatively, we can really gain a lot of information from our data. And so here on the left-hand side, I'm just showing the PI control for CESM1. in the years 800 through 1599. We're looking at just the mean, the annual mean. We can see warmer temperatures across the equatorial regions and cooler temperatures at the higher latitudes. And then on the right, it's just a spectral analysis. And so here what this is just a forward fast Fourier transform that was run on the PI control here for sea surface temperatures. And really what that did was that converted that time variance information into frequency variance. And what we're visualizing here is the peak frequency. And so that's what we're seeing across here. And this pink shading or light purple shading is the annual cycle. So what that means is that globally, or at least for most locations across the globe, the dominant frequency is the annual cycle. And that makes sense, especially for the subtropics, meaning the dominant frequency in our data and our sea surface temperatures is our annual cycle. There are some exceptions to this, though. We see either higher or lower dominant frequencies, particularly across the monsoon region, and also here across the extreme western equatorial Pacific. And these could be associated to monsoon activity or also our warm pool or our double annual cycle out here out west because the sun crosses the equator twice. And so now we performed some freshwater hosing experiments. Were run by our team at in Catalyst, and we can see that here we're visualizing your sea surface temperature anomalies. So we take our experiments and we subtract that PI control that we saw. We're just looking at sea surface temperatures again. And when we focus on the years during these freshwater experiments where the AMOC collapsed and there was no PMOC, we see that overall sea surface temperatures are much cooler across the northern hemisphere and much warmer across the southern hemisphere. And this is a signal that's actually been shown in past studies and is consistent with an AMOC collapse. And there were several experiments that were run. Here I'm just showing 2 experiments for the addition of freshwater across the North Atlantic and the eventual collapse of AMOC. And we're just seeing these freshwater hosing experiments run at 2 different strengths. So 0.2 SV and then, or spear drop, and 0.4 here on the right. But then the question that followed up was, if we're seeing also changes in wind stress, which are represented by these vectors, do we also see a change in let's say, the El Nino Southern Oscillation? Past studies have suggested or shown with other simulations that a change in trade winds could change the signal that we're seeing with ENSO. And so we explored that using our spectral analysis, but I also wanted to highlight some results that were generated using wavelet analysis. And this is also not new, but it was new to me. And so essentially, the reason why we use wavelet analysis instead of a spectral analysis is that with a spectrum analysis, we end up losing temporal information. So we can't see our time series and we can't see how that frequency signal changes over time. We just end up seeing what the dominant frequencies are or what the magnitudes are at certain frequencies. And so that can really mask dominant frequency changes. We can't really visualize them across various frequencies very easily over time. And so what we can do with the wavelet analysis is that we can take a certain wavelet and we can transform our time series to visualize different frequencies over time. And that helps us see how different frequencies are changing and what the dominant frequencies are just in a different way. And so in this case, to perform this analysis, I used the Molina wavelet and followed very similar instructions to those detailed in this paper here, Torrance and Campo. And essentially what a Molina wavelet is, it's just a product of a sine wave and a Gaussian envelope. And then we ran that through the time series. Now, there are numerous different wavelet functions that can be used, but we do know that the Morlet wavelet was better suited for capturing oscillatory behavior in our specific time series, and it offers sufficient resolution for us. I did end up using the seasonal means of our SSTs to reduce the sample across our time series. And so this is what a wavelet analysis output looks like. So what you have is a two-dimensional plane. On the x-axis, you have your time series. So here we're looking at years. And on the y-axis, we're displaying the power of the wavelet transform, from which the dominant frequency can be assessed. So here we have our color bar, and higher values show higher power. These white contours show statistical significance at the 95% confidence level, and that was computed using a white noise background. And what we're visualizing here is that with the control run, at the 1 year, so your annual cycle, you see a very consistent signal. But then if we take a look at our experiments, so these are experiments where freshwater was added to the North Atlantic, eventually collapsing AMOC by the year 200 in both simulations. And here we're also looking at the Nemo 3.4 region sea surface temperatures. We end up seeing a just collapse of that annual cycle signal, at the 1 year period for both global experiments where we added freshwater across the North Atlantic. And so that's really interesting. That shows us that we are seeing that collapse in the annual cycle sea surface temperatures and an increase in the ENSO signal. So between years 2 to 7, just about. So we see an amplification of ENSO when AMOC collapses. And so this has ramifications across the globe. Not only do we have changes associated with AMOC collapsing and global sea surface temperatures, but then you're also looking at modes of variability that are substantially changing. And so here I'm only sharing the results for when AMOC collapses. There are also considerable changes that occur with an active PMOC, so an active overturning circulation in the North Pacific. There are numerous reasons that have been proposed for this happening during an AMOC collapse. There's a paper by Timmerman et al. In 2007 that highlighted this very neat diagram that I really appreciated. And some of the changes that we end up seeing here do occur when the AMOC is collapsed in our simulation as well. So these are quite evident, particularly the weakening of the annual cycle in the equatorial Pacific as a result of the intensification of northeasterly trades. And that can really just be seen by compositing some of these maps and some of these different variables. However, while we assume that these are the reasons, I think moving forward, we should really apply some of these causal effect networks or range of causality, so some of these algorithms that can help us further quantify whether a reason that we think or something that we think is influencing a signal that we're extracting from our data, we should further quantify that using one of these methods. And so that's planned for future work. And so some of the key results from this work, again, I just highlighted very few figures. We see that the tropical Pacific annual cycle amplitude decreases, and we do see an increase in ENSO amplitude. And we saw that this result was consistent whether PMOC or your Pacific meridional overturning circulation developed or not. So that was really interesting to us. And while we did see that some of these potential reasons for ENSO increasing in amplitude were present when AMOC collapsed, even though we got the same signal, so ENSO amplitude increased when PMOC was active, the potential physical reasons were different. So that was quite interesting. In other words, whether AMOC or PMOC are active, yield the same results as far as ENSO amplitude, but the physical reasons behind those changes do differ based on those overturning circulations. So again, I thought that was really interesting. But now moving on to the next project, and I hope I'm doing okay on time. So please do let me know if I need to speed up a bit. But the next project focuses on subseasonal to seasonal prediction, and I'll really just highlight a subseasonal component that I've started working on. And here we're using machine learning and specifically unsupervised learning. And so really what machine learning just is instead of providing the data or using an algorithm that has very specific instructions for what we want output from the data that we're looking at, we really just provide data to some sort of architecture and allow the weights to be trained through a training process. And so the method that I'm using here is an unsupervised technique where we don't have labels. We know that this can be a very powerful approach for us in Earth system science and specifically climate variability studies or predictability, because typically we don't really have labels for our data for what we want. And even if we did, our delineations aren't as stringent or as fixed as they are for, let's say, a cat or a dog. Right, a cat is a cat and a dog is a dog when you're looking at or classifying those sorts of images. But for our cases, those delineations are a bit blurrier and just not as fixed. So here we're using the self-organizing map algorithm. And so this is just an automatic data analysis method, which again is unsupervised. It's been used in numerous applications. It's also not new, even though here I'm citing one of the newer papers. But it's been used in industry and things like finance and linguistics specifically, and also for managing massive text databases. But for our case, we'll be using it to classify various subseasonal patterns related to precipitation. And what's really advantageous about this technique, in addition to not needing labels, is that also we can feed in quite a few variables and work in a very high dimensional space and then map that data or that information to a two-dimensional lattice, which makes it much easier for us to visualize some of these patterns that we can extract from our climate data that we're interested in. And so what we end up having is a two-dimensional lattice, and we're using an input vector of our data, and then this map organizes itself to keep it relatively simple. Overall, as training progresses, the chosen node for each input example is typically called the best matching unit, and that's related to similarity. And the way that this gets trained is that we end up looking at the Euclidean difference between the input vector and all the nodes across this model. And so here I'm showing you some results from a self-organizing map that I trained for precipitation. And so these fields are CESM2 S2S runs that we have completed at NCAR, specifically our collaborator Yaga Richter. Currently this paper is about to be submitted, and the input data for this S2S data is CEFS v2, I believe. And so essentially here what I did was I trained a 3x3 self-organizing map using various input fields, including precipitation anomalies, geopotential height at 500 millibar anomalies based on our S2S climatology, and also used UNV winds at 200 millibars. And so what we're looking at here is an already trained self-organizing map, and we're seeing the maps for just geopotential height for the organized map. And so what we can see here is that we have really distinct synoptic scale patterns that the model has learned and extracted. And so here we see the red is positive geopotential height anomalies. And so overall we have higher pressure either across the eastern US and then lower across the western US. But what's really neat and powerful about self-organizing maps is that we also generally have transitions between our nodes. And some of these that are neighbors are somewhat sort of related based on some of these input variables that we use to train this model. Perhaps more interesting, well, here we are looking at the precipitation anomalies, which are also used as an input field, in addition to the UNV 200 millibar winds. And so again, very distinct patterns and anomalies that we're learning from our self-organizing map. And I also listed the sample sizes on top of each map. So you can see that overall we have a pretty good distribution for each of these nodes that have been trained. What's also interesting is that while we're looking at here week 3, and that's what we use to train the self-organizing map, we can then go ahead and take the indices associated with these maps and look at earlier patterns. So here I can extract outgoing long wave radiation for week 1, and we can see what that looked like across the tropics. And what's interesting is that even though these patterns were not used to train our self-organizing map, they are, I guess, systematic. So we're seeing patterns that emerge preceding these self-organizing maps that were trained. So this is week 1. We can see negative outgoing long wave radiation anomalies or positive. And so these are signals that are across the tropics and preceding our precipitation patterns, suggesting that there is predictability coming from these signals upstream of our precipitation anomaly patterns, and perhaps these could be used for prediction of these patterns. We can also do this for sea surface temperatures. So again, looking at week 1 for our self-organizing map that was trained using week 3. And we have what looks like El Nino on the bottom here and La Nina on the top. But again, there are also some finer scale details in other regions that are important to look at and consider. Something else that I thought perhaps might work, and so I decided to try it, and I think it worked, but I also welcome discussion, I was interested in what would happen if we trained a self-organizing map to organize errors in our CESM2 S2S runs. And so could we pick out some errors that happen in multiple examples, cluster those, and then look at what the upstream patterns are to see if there are some sources of error. Do we have limits in predictability that emerge from our patterns upstream? And so all I did here was I kept it very simple. I just took our precipitation anomalies from our CESM2 runs, again, that were run by Richter and our team. And then I subtracted those by our observations. And for observations, I ended up using a gridded product from NOAA's CPC, so the Climate Prediction Center. And then I just went ahead and created self-organizing maps using those errors. Here I created a 2x3 self-organizing map, so a different dimension. And again, we have our sample sizes above each map, and overall we see a pretty good distribution. And it's quite interesting where we end up picking out some of the larger errors. We have large errors that get grouped across the central plains or southern plains near the Gulf Coast, and also across the Pacific Northwest, or generally just the West Coast, which makes sense. There's likely some higher precipitation events that end up potentially triggering some of these larger errors. So like before, we can now use the indices associated with these maps to pick out our upstream patterns from week 1. And again, we see some signals emerge. And so this would suggest that for some of these regions where we have larger errors across the United States, perhaps some of these upstream patterns result in those errors. Again, it could also be related to model, like systematic errors. So we still need to figure out how to distinguish between those two, whether it really is because of the upstream pattern or just a more systematic issue with our model that we're not considering here. But likewise, we can go ahead and take a look at sea surface temperatures week 1, so a few weeks before the maps that get organized, and we see some patterns emerge for certain nodes within the self-organizing map. So what is next? Future steps. One potential future step, I still need to talk to my team about what they think is the best approach. But something that we briefly discussed is using some sort of semi-supervised approach where we end up using an unsupervised learning method, like the self-organizing maps that we just used here, and use those as labels for a then supervised learning models, such as a convolutional neural network, and then using our input fields to train different classes of precipitation patterns. And this may be perhaps a very useful approach specifically for precipitation, because precipitation is so difficult to predict at weeks 3 and 4. So perhaps if we end up just predicting the patterns, we can gain more skill in that way. Some other questions that I have on this project is whether we can use these methods as well for outlier events and perhaps just focus on extreme precipitation events as opposed to all precipitation events. Something else I didn't mention, I just realized, is that I focus on winter months, or, well, November through March. And so we're not considering other seasons. I'm also curious about whether uncommon synoptic scale patterns get omitted from our self-organizing maps. And that would be, that would pose a very significant limitation for a subsequent convolutional neural network. Because what would happen when it would encounter an uncommon synoptic scale pattern, right, or upstream pattern? And then the other question I have is, when training a convolutional network in our next step, is whether it would be best to use a model that considers the temporal evolution of our predictor fields. So for example, instead of just using week 1 mean as input, should we be using each daily field and using a model that knows that there is a temporal component, and perhaps that evolution of features upstream of the region that we're trying to predict for can provide more skill. There's likely some information there that's getting lost when we just take the weekly mean for our input. And so I think that is all for me. Tom, I'm happy to take questions or suggestions for improvement, or also clarification, because again, this is my first time sharing these results, and so I'm sure I missed quite a few details.
Thank you so much, Maria. So if you have any questions for her, just use the raise your hand button and I can call on you to unmute yourself, or you can type it into the chat box. We'll take the next 20 minutes for discussion.
Thanks, Zach. I saw you clap. Thank you.
I see a question from Tom. Do you want to unmute yourself and ask?
So, yeah, thank you for a great talk and being very pedagogical at the beginning. We especially appreciate it because we're going to make those recordings available on YouTube, and I think this will be a great pedagogical resource. So my first question was about your first project. So I was wondering, for your wavelet function analysis, it seems that you use the Morlet basis function, and there are other possible basis functions, such as the pole or the DOG basis function that will change the shape of your results, how your power spectrum evolve on time. But more generally, my question was, how do you put uncertainty bars on the temporal evolution of your power spectral density that you showed us? How do you determine to what level of precision you determine that temporal evolution of the spectrum?
That's a great question, and I'm not sure I have an answer for you, but let me go to that slide. Oh. Yeah, so that information that you're asking about is not illustrated here, right?
My question is, how do you know if what we're seeing is noise or depends on the Morlet basis function you choose in the evolution? And how do you know something is robust? How do you put quantitative error bars once you have the evolution of the power spectrums that you're showing in this slide?
Okay, great. Yeah, so I tried various different transformations in addition to the Morlet wavelet. There were a few other wavelets that I can't quite recall, but they were all in this Torrance and Campo paper. I'm probably mispronouncing that. But essentially, we still continue to see the same signal. The main change that we would see by using different wavelets was the resolution either across the x-axis or y-axis. So sometimes it'd be just a loss of information in the period or loss of information over time. So, but the main result for me anyway was this erasure or the loss of this annual cycle signal here. And that was evident regardless of what wavelet transform was used. And for statistical significance, I didn't assess some sort of error bars, but we did just end up using the white noise background and assess that at the 95% confidence level. But that doesn't address this question here, right? We're not seeing statistical significance where we have a loss of information. So I would welcome suggestions for how to assess that. Yeah, I guess the reverse of it, if that makes sense. Does that help, Tom?
Yeah, that answers my question on which signal you think is robust across different types of wavelets. Yeah, that was a great answer. Thank you.
We have a question in the chat by John Callahan. Can you clarify briefly how you trained the SOM based on precipitation?
Great, thank you. Okay, yeah, so here I ended up using numerous fields. And so what I did was I just took these specific patterns that you're seeing here, but instead of having just the mean over the sample size, I had the specific week, which was week 3. So I took your week 3 mean for geopotential height at 500 millibars, UMV winds at 200, also looked at precipitation anomalies using the hindcast climatology that we created. Yeah, those were the 4 input variables. And then we end up flattening that vector and train our self-organizing map in that way. And I didn't have to mask out data. I wanted to just keep the fields for the full 2-dimensional space of these maps. And I did try masking out precipitation over water to focus on where we really care about precipitation. But I ended up getting some strange results from that. And so I need to go back and look at what happened there. But essentially just flattened those fields and had a certain sample size of time period. So it was about over 1,000 or so. So not that many based on because we had Monday starts for our S2S hindcasts. And then just use that to train the self-organizing map. For software, I use Minisom. So it's available on GitHub and I highly recommend it. They also have numerous examples on there, like numerous example notebooks, which were very useful for me. But as far as weight initialization, I just did a random initialization and we also use Gaussian and started with like a certain radius, which then decreased. So meaning during earlier training iterations or epochs in like, let's say deep learning, the radius of influence between some of these nodes across the 2D lattice, as an example, when was being assessed by this lattice, there was a greater radius of influence for earlier training iterations than later iterations. And so this competitive learning method was, again, the nodes were influencing each other more to begin with, and then less so as you progress later in the training process. But thank you for your question. I think I need to make a better slide to explain these concepts. Do you have any follow-up? Was that okay?
He says, cool, thanks. I will check out the mini SOM. So I do see a few questions in the chat also for more clarification. So I think I'll go in order on how the questions appear. And if any of you guys who ask the questions want to unmute yourself and kind of clarify or chime in, feel free to. So a question from Antonietta Capotondi. Did you use linear regression for finding the OLR and SST maps at week 1?
No, I just grabbed the variables output by the model. Do you have a recommendation for
Actually,
that?
actually, my question was, you said you use the index associated with your maps to compute the OLR and sea surface temperature patterns. So how did you do that at the previous time?
Oh, great. I think yeah, I probably should have used a different word. By index, I mean, I didn't compute an index. I just extracted the specific time for that went under this certain map. So let's say in this slide that I'm showing here, I have a sample size of 81. So I grabbed those 81 examples that were clustered into this self-organizing map. And then I visualized the week 1 associated with those examples. So I just went back in time for those that matched that, and then just took the mean.
Yeah, so it's actually more a composite than a regression.
Correct. Do you recommend a regression method?
No, I think a composite actually can be better. But
okay, thank you. Nice to meet you.
And I did miss her first question. Are all of your SOMs a complete set?
What does that mean?
So, like, when you compute UFs, for example, you have these patterns and they explain a certain fraction of the variance. So when you do an SOM, so I have no experience with it. That's why it's maybe a very naive question. But so when you do this type of thing, do you actually account for all the possible patterns that you may have? So how much of the variability of your fields is accounted for by the maps that you're showing us?
Yeah, so SOMs are like just another dimensionality reduction method, I guess. And so yeah, it's just data. It just takes in these data examples and groups them. And so what we're looking at here are just more composites. So it's just the 38 composites, and I don't remove any like variability signal or anything beyond just like the climatology anomalies. Does this help at all?
Yeah. No, it's very useful.
Okay.
Thank you very much.
Thank you.
Question from Danny Du. Is 3x3 an optimized one among all the configurations, or you just choose 3x3?
Oh no, that's a great question. I went a little overboard. I tried so many different dimensions. I went 5x5. I think 7x7. At some point, it becomes also important to consider the data size because then otherwise there are too many nodes, and the point of this is to reduce the dimensionality for us to be able to extract the information and understand our data. But yeah, I did try various different shapes. I read in the literature that there's quite a few people that don't use like evenly numbered dimensions. So like instead of using 3x3, use 2x3, let's say. I found some issues with using that for this specific example, not for the example looking at errors. And I'm not entirely sure why, but yeah, there was some sensitivity to that. I would say that as you increase the number of maps that you're considering for training, what you end up seeing is just more maps that are transitional modes between different nodes. So for example, if we have this cyclonic flow here, the neighboring node might have a weaker cyclonic flow. And so again, you just sort of see those transitions a bit more clearly as your lattice grows. Yeah, so I think for these unsupervised methods, maybe a limitation for me anyway. This is really my first application of it for this sort of project. I think a limitation is that we don't really have a great answer for how many categories we would want at the end. And yeah, but I think overall, just having numerous examples and seeing what the signal is that we want to extract from this method. If that helps, hopefully.
We have a question from Effie Fufula. The Morlet wavelet has the best time frequency localization, reaches the limit of Heisenberg uncertainty principle. I assume you use the Morlet wavelet with omega equals 5 as center pass frequency.
Yes. One more time, sorry, my dog.
A question from Effie Fufula. The Morlet wavelet, it has the best time frequency localization, reaches the limit of Heisenberg uncertainty principle. I assume you use the Morlet wavelet with omega 0 equals 5 as center pass frequency.
6, and I just base that on the literature. Do you have a recommendation?
I don't see any comment back from her, and she may have left this as well. So
Oh, okay. Thank
yeah.
you for that. That was a great question.
Yeah, I can put you in touch with her afterwards.
Thanks.
So do we have any other questions for Maria? Maybe her dog as well. All right, Mike Pritchard, go ahead.
Hi, thanks. Really enjoyed your talk.
Mike.
Hey, yeah, I had a question, just like a process question. I'm wondering, what challenges do you foresee in the nearest term steps that you mentioned that you're really interested in? Like, I'm thinking about how approachable is the causal inference machinery from where you sit for the part 1 work to stress test that process chain, and in part 2, I think it sounded like you're planning to take the low dimensional labels and try to predict them using nice maps or maybe even animations on the front end. And if that's the case, I always wonder about how people who deal with real observations get around the sample size limit, and whether you have any data augmentation methods in the back of your mind that you're thinking of for that. But yeah, could you just maybe talk in general about the technical challenges for the next part?
Excellent. Yes, great questions. Yeah, and I'll probably have to ask you again about question 2, but I already have an answer in mind. But for question 1, yeah, for the technical challenges, it'll be my first time applying a causal inference technique. And I've been looking forward to this day. So I'm not fully sure I know yet what the challenges are. I know I'll have to, process some time series depending on the method that I approach. And there are different levels of complexity moving forward into, let's say, like graphs that we're using and the number of variables that we're trying to explain. I think one of the challenges that I am somewhat worried about is how accurate a representation of a process that we are saying is influencing that a certain outcome really is. So for example, if I were looking at the shift in trade winds, how would I, categorize, how do I create a time series of a shift in trade winds? The region might change, right? And so I think those are the general concerns I have, if that makes sense. It might be that the same reason is resulting in a certain outcome, but the reason might have moved around, or yeah, and how do I make sure I'm accounting for that in a really large data set? Because again, we're looking at 800 years. It's not like I'm going to be able to go back and quality check each one. So that's something that I'm concerned about. Yeah. And then for the second question, one more time.
Oh, I was just wondering, well, I guess I wanted to clarify, are you, now that you think you see a precursor signal in the OLR field that might predict a few weeks in advance one of these clusters, is the idea to try to see if you can task a neural network with that prediction in a totally data-driven way? And if so, then, unlike the kind of work that I do that tries to build these regressions from like hundreds of millions of climate model output samples, then if it's a predictability issue, then you're stuck with the number of observed samples. And so, in image processing, people rotate and translate images to get around limited numbers of samples. And I'm wondering if you have thoughts for how to boost the sample size, but I might be missing what you're actually planning to do entirely.
No,
yeah.
Yep, you're totally right. I was thinking for I think framing the way that we frame the problem as far as the input and output is really important. And I was thinking one way to potentially augment the sample size would be just to offset the week mean. And so let's say I'm right now I'm using the fixed week 3, right? So whatever that day is and the end of that. So if we shifted it by a day or two and just increase in that way, but then what we're using as input would matter as well too, right? Because I don't have, from day 0, there's nothing before that in our initialized runs. So perhaps using observations in that case would be more strategic if we're trying to augment in that way with the model output. So that was one way I was thinking. I remember you mentioned the video prediction. That's an idea for the input. But again, I think the overall challenge will be data size. And so we'll see how we address that moving forward. But my naive first try is shifting the weeks around a little bit.
Cool, thanks.
And I welcome suggestions as well. Thank you.
Okay, so we have 1 minute left. Do we have any final questions or comments for Maria?
May I ask a question about the very last step? I think, so I may have missed it, but once you reduce the dimensionality of the error, of the different error modes that you see in your prediction, how did you plan on using them moving forward? Was it to do some kind of post-processing at the subseasonal scale? Or was it mostly for insight and diagnostic purposes? What was your plan moving forward?
Thank you for that question. That's great. So my thinking was to do a similar approach to this and do prediction of the errors. And this is also probably naive. We'll see how it goes. But then using explainable methods such as LRP or saliency maps, and then going back into our input fields and seeing if we see signals pinpointed for one, if we're predicting precipitation, where sources of predictability are coming from, and 2, if we're predicting precipitation error predictions. If we're doing that, then do we see limits of predictability from a certain region in our map? So just the same question, just flipped. Sources of predictability and limits of predictability, with my general thinking.
Thank you.
All right, I think that will conclude today's webinar. So thank you so much, Maria, for your talk. And thank you for everyone who's on the line and for asking and contributing questions. Coming up in 2 weeks, we'll have a talk by Jakob Runge of the German Aerospace Center. His talk is entitled Causal Inference in Earth System Sciences. So I hope to see you at that point. For a recording of Maria's talk, that will come later this week, and I'll send out an announcement when that is available. So again, thank you so much, Maria, for your talk.